Section 1.3, we're going to look at ways to describe quantitative data. And most of this stuff is going to be things that you are already familiar with and have seen before. So we're talking about numbers that we can use to describe data. So the first one is the mean, okay? Or the average. Nothing tricky here. You've seen this before. Add all the numbers up, divide them by the total number of data values. All right, so we have an example here. Um, we have the number of goals scored in 20 games by the U.S. women's soccer team. Okay, and we see this dot plot. The average is 3.15 goals. But if we look at this dot plot, we can see that out here, the one game they scored 9 and one game they scored 10. Those appear to be outliers. So what we want to know is what would happen if we took those numbers out and found the mean of all the other games. Okay, so we eliminate the 9 and the 10, and now the mean is 2.44. That's a rather large difference. It's more than half a goal per game, which is kind of a big deal in soccer. Okay, so what this tells us is that the mean is sensitive to outliers. Okay, if there are outliers in a data set, they will have a large effect on the mean. Another way of saying that is the mean is not a resistant measure. Okay, so outliers can affect the mean. Another way that we have of measuring the middle of the data is the median. Okay, again, something you have seen before. It is the middle number in a data set when we arrange them from smallest to largest. Okay, so we put it in numerical order from 1 to 10, and you're probably familiar with like the cross out method where we cross out the first number, second to last number, and so on. And so we get down to the middle, and then if it's an even number of data points, then we'll have 2 left over, and we find the average of those 2 points, and that is our median. Okay. Um, Something that you need to be able to do when looking at a data set, even if you don't know the numbers, is to compare the mean and the median. So in this data set, for the mean, if we took out those outliers of 9 and 10, it dropped from 3 to 2.4. Okay. However, if we took out these outliers of 9 and 10 and found the median, it would still be 2. So the median is resistant to outliers. Okay. Outliers don't really have that big of an effect on the median. So what that means is the shape of a distribution will tell me something about the relationship between the mean and the median. Okay, so in a symmetric distribution, all right, when the distribution is roughly symmetric, the mean and the median are going to be pretty close to each other. They're going to be roughly equal. They may not be exact, but they're going to be pretty close to each other. Okay, that's because there are no outliers, or at least the outliers aren't specific to one side of the distribution. So the middle, both the mean and the median, give me a good idea of the center of the distribution. Okay. If my distribution is skewed left, like this one up here, these lower outliers are going to pull the mean down. So the mean is going to be less than the median when my distribution is skewed to the left. And then, of course, the opposite, if my distribution is skewed to the right, these high outliers pull my mean towards them, so the mean would be greater than the median. Okay, so this is just a summary of what we just talked about. Um, when distributions are skewed, the mean is pulled in that direction. So if it's skewed left, mean is less than median. If it's skewed right, mean is greater than median. Okay, the median is resistant to outliers, but the mean is not. Okay, so just like we had 2 ways to measure the center, the mean and the median, we also have 2 ways that we're going to look at to measure variability. And one of those is the range. Okay, so again, something that you are most likely familiar with. Biggest number minus smallest number. Okay, that will give me the range. One thing that you want to be careful with is make sure you write your answer as one number. So the range is 9. The range is not 10 to 1 or 1 to 10. Okay, the range is also not a resistant measure because again, we're doing the largest number and the smallest number. So if either of those are outliers, that's going to have a large effect on my range. A second way that we can measure variability is standard deviation. Again, something you are familiar with. It has this big scary formula with the summation where we have to do a whole bunch of math, but honestly, I would just do it on your calculator every time, and we'll talk about how to use your calculator for that in class. It is part of the one variable statistics. So if you know how to find that, if you remember how to do that from another class, that's where you can get standard deviation from, because otherwise it's a whole big mess. So things you need to know about standard deviation. It has to be greater than or equal to 0. The only way it could be equal to 0 is if every number in the data set is exactly the same. So if my data set is 5555, then I would have a standard deviation of 0 because there is no variation. Every number is the same. All right. Standard deviation is also not resistant. Okay. And it measures variation about the mean. So when you are asked to interpret standard deviation, what you should say is the typical value or the value typically varies by whatever your standard deviation is. So if my standard deviation is 4.2, then the number of goal scores typically varies by 4.2 from the mean. Okay. A third way that we have of measuring variability is interquartile range, or IQR. Again, you've probably seen this before. Quartiles, so we have the median. The median is technically the second quartile. So the first quartile is the median of the lower half, and the third quartile is the median of the upper half. And if we do Q3 minus Q1, that gives me the interquartile range, or IQR. Again, quartiles are something that you can be found in the 1 var stats in your calculator. And again, I'll remind you how to do that, but if you know how to do it, then you can see where that comes from. Okay, so here we have an example. We have travel times for 20 New Yorkers. They put the things in order. They found the median. They found Q1 and Q3, and then you subtract those two numbers, and that is the IQR. All right, and so here's how you would write an interpretation sentence if you were asked to interpret the IQR. The range of the middle half of travel times for New Yorkers is 27.5 minutes. All right. One other thing that we can use IQR for is identifying outliers. Okay, there's a couple different rules for outliers, but right now this is the one we're going to talk about, which is the 1.5 times IQR rule. Okay, so we find IQR, and then when we look for low outliers, we're going to do Q1 minus 1.5 times our IQR. Any number lower than that would be considered an outlier. And then for high outliers, we're going to do Q3 plus 1.5 times IQR, and any number higher than that would be considered an outlier. So we'll look at an example. It's that same data set from before. And here we have Q1 is 22.2, Q3 is 22.6, so the IQR is 0.4. Okay, so when I do this math to find my low outliers, I'm going to do Q1, 22.2, minus 1.5 times my IQR, and that gives me 21.6. So that means any number in my data set that is lower than 21.6 is an outlier. So we have one here at 21.5. We can do the same thing in the other direction with Q3. So I do Q3, 22.6 plus 1.5 times my IQR. And that means any number that is larger than 23.2 is an outlier. Okay. So then I have two outliers in this data set, and we always need to say what rule we're using because we'll talk about like a 2 standard deviation rule later. All right, so whenever you write these answers, make sure you're talking about which rule you're using, and in this case, it's the 1.5 times IQR rule. Okay. Why should we look for outliers? They could be inaccurate data values, okay? Data can get entered incorrectly. It can get written down incorrectly. Lots of different things can happen. They can indicate a remarkable occurrence. So, you know, something super rare happened, and an outlier would tell us that. And then the biggest thing is they have a huge influence on mean, range, standard deviation. So we need to acknowledge those so that we can see where our data might be skewed. Last thing we're going to do is look at box plots. You have seen these before. You might have called them box and whiskers. All right. So first thing we need to do is find the 5-number summary. The 5-number summary is these numbers: the minimum, Q1, median, Q3, maximum. Again, all available in that 1 var stats in your calculator. Okay. Then we need to identify outliers. All right. And we're going to use the 1.5 times IQR rule. This is something you may not have done before. In this class, when we do box plots or box and whiskers, we're going to mark the outliers separately. We're not going to include them as part of our box plot. Okay, so I know that my line has to go at least from 21.5 to 23.3 because that's my max and min in my data. All right, so those are my outliers. I'm going to make a number line, and I'm going to make sure that those numbers are included. I'm going to draw a box from Q1 to Q3, and then I'm going to put a line in the middle for the median. My whiskers are going to go out to the last data value that isn't an outlier. Okay, so we had our outliers of 21.5 and 23.4, I think they were, or 3. Okay, those are our outliers. The next lowest data point, that's going to be my new min. The next highest data point is going to be my new max. Okay, so we're always going to label outliers separately, either with a little asterisk or a dot in any box plot that we make. Okay, and that is going to be it for 1.3.